When wiring a pump controlled by a magnetic starter located remotely with a long conduit run between the starter and the pump, several national electrical code considerations and industry practices come into play. NEC 300.3 C addresses the installation of conductors in raceways, emphasizing that conductors should not be installed in a way that magnetic forces from the circuit will damage the conductor or its insulation. This is particularly relevant when dealing with motor circuits due to the higher currents involved. NEC 430.113 states that conductors supplying a motor must be protected from mechanical injury and secured against vibration. This is important for ensuring the long-term reliability and safety of the installation. There are two common industry practices for addressing these concerns. Firstly, the method of bundling conductors and running them in the same conduit. In this method, bundle the motor leads and control wiring together. Secure the bundle firmly to the conduit to prevent movement. Use cable ties or other approved methods to secure the bundle at regular intervals along the conduit run. Secondly, the method is to separate conduits for motor leads and control wiring. This involves running the motor leads and control wiring in separate conduits. Secure each conduit firmly to prevent vibration. Provide adequate separation between the two conduits to minimize magnetic interference. Both methods are generally acceptable, but each has its advantages and disadvantages. Method 1, bundling conductors, is often more cost-effective because it requires less material and labor. However, it necessitates more secure bundling to prevent damage from magnetic forces. The magnetic fields generated by the motor conductors can induce currents in the control wiring or cause the conductors to vibrate against each other, potentially damaging the insulation over time. Method 2, using separate conduits, is more robust in terms of minimizing magnetic interference and potential damage. By separating the motor leads and control wiring, the magnetic field from the motor conductors has less of an impact on the control wiring. However, this method requires additional materials, such as extra conduit and fittings, as well as more installation time. In addition to these methods, consider a few additional recommendations for wiring pumps with magnetic starters. Use flexible conduit, such as liquid-type flexible metal conduit for the pump connection. This allows for vibration and movement of the pump without putting stress on the conductors or conduit. Mount the pump and starter firmly to prevent vibration and reduce the risk of damage to the wiring. Vibration can loosen connections and cause conductors to rub against each other or the conduit. Consider using shielded cables or conduits to minimize magnetic interference, especially if sensitive control circuits are involved. Shielded cables or conduits can help to contain the magnetic field and prevent it from affecting other equipment. To elaborate further on NEC 300.3 C, the magnetic forces created by the circuit conductors can induce eddy currents in the surrounding metal, such as the conduit. These eddy currents can cause the metal to heat up, which can damage the conductor insulation and potentially create a fire hazard. Additionally, the magnetic forces can cause the conductors to move or vibrate, which can also damage the insulation over time. Therefore, it is important to minimize the magnetic forces by properly bundling the conductors or using separate conduits. When bundling conductors, it is important to use cable ties or other approved methods to secure the bundle tightly. This will help to prevent the conductors from moving or vibrating. It is also important to use the correct size and type of cable ties. The cable ties should be strong enough to hold the conductors securely, and they should be made of a material that is compatible with the environment. For example, if the conduit is exposed to sunlight, the cable ties should be made of a UV-resistant material. When using separate conduits, it is important to provide adequate separation between the two conduits. This will help to minimize the magnetic interference between the motor leads and control wiring. The amount of separation required will depend on the size of the conductors and the amount of current flowing through them. A general rule of thumb is to provide at least 12 inches or 304.8 millimeters of separation. To further comply with NEC 430.113 A. Ensure that the conductors are protected from mechanical injury. This can be achieved by using conduit or other approved raceways. A raceway should be sized appropriately for the number and size of conductors it contains. The raceway should also be securely fastened to the building structure to prevent it from moving or vibrating. When using flexible conduit for the pump connection, it is important to use a liquid-tight type of flexible conduit. This will help to protect the conductors from moisture and other contaminants. The flexible conduit should be sized appropriately for the number and size of conductors it contains. The flexible conduit should also be securely fastened to the pump and the conduit system. When mounting the pump and starter, it is important to use vibration isolation pads. These pads will help to absorb the vibration from the pump and prevent it from being transmitted to the building structure. The vibration isolation pad should be sized appropriately for the weight of the pump and starter. They should also be made of a material that is compatible with the environment. When using shielded cables or conduits, it is important to properly ground the shield. This will help to prevent the magnetic interference from affecting other equipment. The shield should be grounded to a common ground point with the equipment it is protecting. The grounding conductor should be sized appropriately for the size of the shield. When selecting conductors for the pump motor circuit, it is important to consider the motor's full load current rating and the ambient temperature. The conductors should be sized to carry at least 125% of the motor's full load current rating as required by NEC 430.22. This will help to prevent the conductors from overheating. The conductors should also be derated for the ambient temperature as required by NEC 310.15. This will help to ensure that the conductors can safely carry the current in the given environment. When selecting overcurrent protection for the pump motor circuit, it is important to consider the motor's full load current rating and the type of motor. The overcurrent protection should be sized to protect the conductors from overload and short circuit. The overcurrent protection should also be sized to allow the motor to start without tripping. NEC 430 provides specific requirements for motor overcurrent protection. For example, inverse time circuit breakers are commonly used. The maximum rating or setting for an inverse time circuit breaker is typically 250% of the motor's full load current for design E motors. When installing the magnetic starter, it is important to follow the manufacturer's instructions. The magnetic starter should be mounted in a location that is protected from moisture and other contaminants. The magnetic starter should also be properly grounded. The control wiring for the magnetic starter should be installed in accordance with NEC 725, which covers remote control, signaling, and power-limited circuits. This article provides requirements for conductor size, overcurrent protection, and wiring methods. If the pump is located in a hazardous location, such as a Class 1, Division 1 or 2 location, it is important to follow the requirements of NEC 500 through 516. These articles provide requirements for electrical equipment and wiring in hazardous locations. In summary, when wiring a pump with a magnetic starter, it is important to consider NEC 300.3, C, NEC 430.113, A, and industry best practices. By following these guidelines, you can ensure a safe and reliable installation. Consider bundling conductors versus using separate conduits and utilize additional recommendations. Always adhere to the latest edition of the NEC and consult with a qualified electrical professional if you have any questions. Remember to check local codes and regulations as they may have additional requirements. Proper grounding is crucial for safety and to prevent electrical noise from interfering with the control circuits. Use appropriate grounding conductors and ensure they are properly connected to the grounding electrode system. Also, consider the use of surge protection devices to protect the motor and control equipment from voltage surges. These devices can help to prevent damage from lightning strikes or other transient voltage events. Always use approved materials and equipment that are listed by a recognized testing laboratory, such as Underwriters Laboratories or ETL. This will help to ensure that the equipment meets safety standards and is suitable for the intended application. Finally, remember to document the installation thoroughly, including wiring diagrams, equipment specifications, and test results. This documentation will be helpful for future maintenance and troubleshooting. Also, remember when securing the conduit runs themselves to use appropriate hangers and supports. These should be installed at intervals that meet or exceed NEC requirements. Properly supported conduit prevents stress on connections and reduces the likelihood of vibration-related issues. Where the conduit enters or exits enclosures, use proper fittings such as bushings and connectors. Bushings protect the conductors from abrasion as they pass through the metal edges of the enclosure. Connectors provide a secure and grounded connection between the conduit and the enclosure. Also ensure that all electrical connections are made properly, using appropriate connectors and terminals. Loose or corroded connections can cause overheating and voltage drops, which can damage the motor and control equipment. Use torque wrenches to tighten connections to the manufacturer's specifications. Perform routine maintenance on the pump motor and control equipment, including checking connections, cleaning contacts, and lubricating moving parts. Regular maintenance can help to prevent problems before they occur and extend the life of the equipment. In areas subject to physical damage, consider using rigid metal conduit or other forms of mechanical protection for the wiring. This will help to protect the conductors from impact and abrasion. When running conduit underground, be sure to follow NEC requirements for burial depth and protection from physical damage. Use appropriate warning tape or markers to indicate the presence of underground wiring. Also, when working with electrical equipment, always follow safe work practices. Wear appropriate personal protective equipment, such as safety glasses and gloves, to energize and lock out the circuit before working on it. Use a voltage tester to verify that the circuit is de-energized. Never work on electrical equipment when you're wet or standing in water. The NEC is updated every 3 years, so it is important to stay up to date on the latest requirements. Attend continuing education courses and read industry publications to stay informed. When making any changes to the electrical system, be sure to obtain the necessary permits and inspections. This will help to ensure that the work is done safely and in accordance with code. If you are not qualified to perform electrical work, hire a licensed electrician. Electrical work can be dangerous, and it is important to have the right skills and knowledge to do the job safely. Also, remember to label all electrical panels and circuits clearly. This will help to make it easier to identify and troubleshoot problems in the future. Use a permanent marker or label maker to create clear and legible labels. In addition, consider the environmental conditions when selecting electrical equipment and wiring. For example, if the pump is located in a corrosive environment, use equipment and wiring that is rated for that environment. The National Electrical Code Article 430 covers motors and motor circuits. Article 430.52 specifically addresses the rating or setting for individual motor circuit short circuit and ground fault protection. This section provides tables and guidelines for selecting the appropriate overcurrent protection device based on the motor's horsepower rating, voltage, and type of motor. The type of motor and its corresponding code letter designation impacts the selection of overcurrent protection. The code letter indicates the motor's locked rotor current, which is a critical factor in determining the appropriate fuse or circuit breaker size. Different types of motors have different starting characteristics, and the overcurrent protection must be sized to allow the motor to start without nuisance tripping while still providing adequate protection against short circuits and ground faults. Consider motor contribution to fault current. When a fault occurs in a motor circuit, the motor itself can contribute to the fault current. This contribution needs to be taken into account when coordinating the overcurrent protection devices to ensure proper selectivity and prevent cascading trips. Use selective coordination to isolate faults. Selective coordination is a design approach where overcurrent protection devices are coordinated to isolate a fault to the smallest possible portion of the electrical system. This minimizes downtime and prevents unnecessary interruption of power to other loads. The National Electrical Code provides guidelines for selective coordination, but it is often necessary to perform a detailed coordination study to ensure that the system is properly coordinated. In addition to motor overload protection, it is important to provide adequate short circuit and ground fault protection. Short circuit protection is designed to quickly interrupt high-level fault currents, while ground fault protection is designed to detect and interrupt low-level ground faults. Both types of protection are essential for preventing damage to equipment and ensuring safety. Use ground fault circuit interrupters where required. Ground fault circuit interrupters are required in certain locations, such as bathrooms, kitchens, and outdoor areas, to protect people from electric shock. GFCIs are designed to detect small imbalances in current and quickly interrupt the circuit. Perform a motor starting study. A motor starting study is a detailed analysis of the voltage drop and inrush current that occur when a motor is started. This study can help to determine the appropriate size of conductors, transformers, and overcurrent protection devices. It can also help to identify potential problems such as voltage flicker that may occur during motor starting. Consider the impact of harmonics. Harmonics are distortions of the sinusoidal waveform of alternating current. They can be caused by nonlinear loads such as electronic devices and variable frequency drives. Harmonics can cause a variety of problems, including overheating of equipment, increased energy losses, and interference with communication systems. If harmonics are present, it may be necessary to install harmonic filters to mitigate their effects. Use appropriate wiring methods for the environment. The wiring methods used in a motor circuit should be appropriate for the environment. For example, in wet locations, use watertight conduit and fittings. In hazardous locations, use explosion-proof equipment and wiring methods. Comply with all applicable codes and standards. Motor circuits must comply with all applicable codes and standards, including the National Electrical Code, state and local built-in codes, and industry standards. It is important to stay up to date on the latest codes and standards to ensure that the motor circuit is safe and compliant. To ensure that electrical installations are safe and reliable, thorough testing and commissioning procedures are essential. These procedures verify that the equipment is functioning correctly, that wiring connections are secure, and that protective devices are properly calibrated. Document all testing and commissioning activities, including the results of tests and any adjustments made to equipment. This documentation provides a valuable record of the installation's condition and can be useful for troubleshooting future problems. Perform routine inspections of electrical equipment to identify potential problems before they lead to failures. Inspections should include visual checks of wiring, connections, and equipment enclosures, as well as electrical tests to verify proper functioning. Address any issues identified during inspections promptly to prevent them from escalating into more serious problems. Keep electrical equipment clean and free of debris. Dust, dirt, and other contaminants can accumulate on electrical components and cause them to overheat or malfunction. Regular cleaning can help to prevent these problems and extend the life of the equipment. Ensure that electrical equipment is properly ventilated to prevent overheating. Overheating can damage electrical components and reduce their lifespan. Make sure that ventilation openings are not blocked and that cooling fans are functioning properly. Provide adequate space around electrical equipment for maintenance and repairs. This will make it easier to access the equipment and perform necessary work. Do not store materials or equipment in front of electrical panels or other electrical equipment. In addition, in motor control circuits, auxiliary contacts on contactors and relays play a crucial role in providing feedback and interlocking functions. These contacts are used to indicate the status of the device, such as whether it is open or closed, and to control other devices in the circuit. Use auxiliary contacts for interlocking functions to prevent conflicting operations. For example, an auxiliary contact on a motor starter can be used to prevent another motor from starting if the first motor is not running. Monitor control circuit voltages to ensure that they are within acceptable limit. Low voltage can cause control devices to malfunction, while high voltage can damage them. Use a voltmeter to check control circuit voltages regularly. Use surge protection devices to protect control circuits from voltage spikes. Voltage spikes can damage sensitive electronic components and control circuits. Surge protection devices can help to prevent this damage by diverting excess voltage to ground. Use shielded cables for control circuits to reduce electrical noise. Electrical noise can interfere with the operation of control circuits and cause them to malfunction. Shielded cables can help to reduce this noise by blocking electromagnetic interference. Isolate control circuits from power circuits to prevent voltage transients from damaging control devices. Voltage transients can be caused by switching operations or other disturbances on the power system. Isolation can be achieved by using separate transformers or optoisolators. Also use proper wire management techniques to keep control circuits neat and organized. This will make it easier to troubleshoot problems and maintain the circuits. Use cable ties or other fasteners to secure wires and prevent them from becoming tangled. Label wires clearly to identify their function. This will make it easier to trace circuits and troubleshoot problems. Use terminal blocks to provide a convenient and organized way to connect wires. Terminal blocks allow wires to be easily connected and disconnected without having to splice them. Inspect control circuits regularly for loose connections, damaged wires, and other problems. Loose connections can cause intermittent problems and can lead to equipment failure. Damaged wires can create a safety hazard. Also, train personnel on proper lockout/tagout procedures to ensure that control circuits are de-energized before maintenance is performed. Lockout/tagout procedures are designed to prevent accidental energization of equipment during maintenance. The last point to consider: design control systems for redundancy to improve reliability. Redundancy involves using multiple components of systems to perform the same function. If one component fails, the other component can take over, ensuring that the system continues to operate.